Last class we talked about the integral test, which was a way of comparing a series to a corresponding integral to figure out whether or not the series converged. Today we're going to look at a couple different tests that will also help us determine whether or not a given series converges. The first one we're going to look at is called the direct comparison test. And the idea is if we have two sequences that are both positive, but we know that a sub n is always at least as big as b sub n, then we can compare the two series. And if we know that a sub n converges, then b sub n has to converge as well. Intuitively, that should be pretty clear because we know that a sub n is even bigger than b sub n. And so if a sub n is bigger, but it's still a finite number, then b sub n has got to be a smaller finite number. On the other hand, if b sub n diverges, then we know that a sub n is even bigger than that, so the sum of the a sub n has to diverge as well. Let's see how we can use this in a couple examples. So the first one is this series from n equals 1 to infinity of 1 over n minus pi. And so this pi right here, because it's a constant, is probably not going to affect the behavior of the series overall. And so we might predict that this series is going to diverge because we already know that 1 over n diverges. But the question is, how do we show that more rigorously? And the idea is that 1 over n minus pi, because we're subtracting off a pi, that's making the denominator smaller, which overall is making the whole function bigger. And so this has to be greater than 1 over n. That's assuming that n is bigger than pi, because otherwise the left-hand side might be negative. But I only care about this for large values of n anyway. And so we have this inequality, and we also know that 1 over n is always greater than 0. And so now, by the direct comparison, since 1 over n diverges, and at this point we can say that this is true by the p-test, then we also know that 1 over n minus pi diverges by direct comparison. And so I really do want to get in the habit of writing down all of the tests that I'm using in these rational breakdowns of why a series converges or not. Okay, let's look at the next example where we have the sum from n equals 4 to infinity of 3 over n 2 to the n. And so here first I want to think about what's the biggest function in play in the numerator and the biggest function in play in the denominator, because they're going to drive whether or not the series converges or diverges. In the numerator, there's just a constant, so that doesn't make much of a difference. But in the denominator, this 2 to the n is going to be way bigger than the n term here. And so overall, it's probably going to be pretty close to 3 over 2 to the n. And that's just a geometric series. And so I already know that that's probably going to converge. And so now the question is, how do I deal with this n out front to sort of verify my reasoning? And the point for the direct comparison is that that n only makes stuff smaller. And so here I can see that 3 over n times 2 to the n is just less than or equal to 3 over 2 to the n. And also, this is positive. And since the sum of 3 over 2 to the n converges, because it's geometric, with r equaling 1/2, which is less than 1, then we know that my original series, 3 over n times 2 to the n, converges by direct comparison. All right. And so here it's really important that we ended up finding a series that was bigger than the series that we cared about that also converged. And so in general, the first step to one of these problems is you're going to have to make an educated guess about whether or not you think the series you're looking at converges or diverges. If it converges, then you're going to want to find something bigger that still converges if you're going to use the direct comparison test. If it diverges, then you want to find something smaller that diverges. Let's look at this one other example here, the 1 over n to the 1.5. I'm going to show a bad way of trying to show that this does something. And so here, 1 over n to the 1.5, you might be tempted to say that that's less than 1 over n. Right? But we know that this series of 1 over n diverges because it's the harmonic series, or by the p-test. And so the point is, if we tried to make this comparison, it just doesn't help. Because at this point, all we've seen is that the sum that we care about is smaller than something that diverges. And so that doesn't tell us whether or not my original series converges or diverges. It could still do either one. And the point is that we'd have to do a better, different comparison or a different rule in order to figure out what happens here.